We proved that the Carnot-Caratheodory distance we've put on H1 does make it a metric space indeed. To prove that this is a metric space, the properties of symmetry and the triangle inequality are actually quite straightforward from the very definition itself. What remains to be proved, and is not that easy, is actually the fact that this distance is finite and positive if P is different from Q. In the past few lectures, we have studied the behavior of horizontal curves under the orthogonal projection pi, and we have used it to identify some special cases of horizontal curves. In particular, we have seen that the length of a horizontal curve is equal to the length of its projection calculated in the Euclidean geometry of the plane. And also we have seen that if we have any absolutely continuous curve in the plane, we can lift it and find a horizontal curve. In the very special case where we take the planar curve to be the arc length parameterization of a circle, the horizontal lift, the horizontal curve coming from the lifting, joins two points which are different only by a vertical difference. On the other hand, we've seen that any line from the origin to any other point on the plane can be parameterized to be a horizontal curve. To prove the finiteness of Carnot-Caratheodory distance, it is enough to show that any point can be connected to the origin by a horizontal curve. And that is easy given the previous cases. First, we project P to the plane, and then we join it to the origin by the straight line. We also take the horizontal lift of the circle with the right area so that its lift connects P to its projection. Therefore, concatenating these two paths gives us one horizontal curve from the origin to P. And the final result becomes that DCC of 0, the origin to the P, is by definition infimum of all horizontal curves. So this will be the length of this particular gamma, which corresponds to concatenating the two pieces. And we've seen that each one of these has a finite area. Indeed, it's the length of the line plus the perimeter of the projection of the other piece, which is a circle. So in any case, we're only interested in proving that it's finite. So for DCC of P and Q, we can concatenate two such curves, and that will be distance from 0 to P plus distance from 0 to Q, and again it will be finite. Now we must show that the distance of 2 points can be 0 only if they are equal. Recall that the Carnot distance is always bigger than the distance of projections in the plane. This forces the projection of 2 points to be equal, and without too much loss in generality, let's say they are on the t-axis. From definition, it follows that for every epsilon small, we can find a horizontal curve from P to Q whose length is less than epsilon. And remember that for any horizontal curve, the length is equal to the length of projection of the curve. If you write gamma and gamma bar, the projection onto the xy plane in coordinates, then gamma bar is a loop on the plane coming back to the origin. Now remember the key fact that T2 minus T1 equals this special integral over the projection. At this point, one can argue that because gamma bar has length very small, by isoperimetric inequality, its area should also be quite small. And that area is equal to here. Therefore, T2 minus T1 should be arbitrarily small. But I want to avoid use of isoperimetric inequality because it's not at all a trivial fact, and we don't have a precise statement for it. So let's avoid big machinery as far as we can. Without isoperimetric inequality, we continue as follows. Because the length of curve is bounded by 1 and the curve starts at 0, the whole image should be contained within a finite ball. Therefore, the values x and y should be bounded by some constant m, which is independent of gamma. The only restriction is gamma has length less than epsilon. Now, how does this help us? Well, from the above equality, then we can say that T1 minus T2 is bounded by some constant which depends on m, integral over gamma bar of x prime s plus y prime s ds. And that in turn is less than some other constant, universal, over gamma bar of the square root of x prime of s to the power 2 plus y prime of s to the power 2 ds. But this is equal to the Euclidean length of gamma bar, which is equal to the length of gamma in the Sub-Riemannian metric, and that was assumed to be less than epsilon. So we have shown that for every epsilon positive, we can make T2 minus T1 less than epsilon, and that implies T2 equal T1 as well. Now that we have a metric space for ourselves, we can ask interesting questions about its geodesics, about its Hausdorff dimension. I'll probably dedicate 1 or 2 more videos to this, but at some point we have to say goodbye to the Sub-Riemannian structure and also talk about the Lie group aspect of the Heisenberg group. If you have any questions or suggestions, please put them in the comments. Thank you for watching and have a good day.